Welcome to today's broadcast of the Phillies Emergency Teaching Network. Today is February 13, 2014, and as you can see, I am broadcasting solutions to the homework problems we cannot do in class today because there's a snowstorm. The problems we are going to be broadcasting start with problem A-36, a mass moving under the influence of an external force. A-37, a box sliding down an inclined plane, and we ask how fast it's going. Then, of course, there is problem A-38, where we compress a spring and ask what happened. And eventually, we reach problem A-40, and problem A-40 is a box sliding down a plane under the influence of friction. Problem A-40 is a lot like problem A-37, except for the friction force. Problem A-36A, we worked in class. Problem A-35, another scene from the motion picture production. G, we worked that in class last time, and we will now be proceeding with the actual problems. We have now reached problem A-36. We have a mass that has acting on it a force 3 plus 2x in the I-hat direction. Of course, that is a force, so it's a vector. The particle moves from x equals 15 to x equals 10. And we ask what work was done on the particle, and also could the initial kinetic energy have been 0? Could the particle have been at rest at x equals 15? Let's calculate the work done first. General formula, the work is integral dx f of x. F sub x is the x component of the force. Remember, components are scalars, not vectors, so the x component of the force, as seen in the next line, is 3 plus 2x, not 3 plus 2x times I hat. The particle proceeds from x equals 15 to x equals 10, so we do an integral from 15 to 10. The integration itself, just we're integrating a polynomial, the integration itself gives us 3x plus 2x squared over 2, evaluated from 15 to 10. We set up the evaluation. The evaluation is the final value of the function minus the initial value of the function. The final value of the function is the function evaluated at x equals 10. The initial value of the function is the value of the function at x equals 15. You turn the crank, and out comes the total work done, negative 140 joules. Okay, so the work done is 140 joules, and minus 140, would be better watch that sign. And thanks to the work-energy theorem, we know that the work done is Kf minus Ki. Kf minus Ki is negative, so the final kinetic energy must be 140 joules less than the initial kinetic energy. G, the final kinetic energy can't be negative, can it? No. If it was, the velocity would have to be imaginary, or the mass would have to be negative. That's very bad. And therefore, the kinetic energy initially must have been positive, and it must have been greater than 140 joules. That's it. Here we are with problem A-37. We have a box at the top of a frictionless ramp. It slides a distance down the ramp, and we'd like to know how fast the box is going when it reaches a distance down the ramp. So here's the box, and it has a mass. It's going to go from x equals 0 to x equals 3. The ramp has an angle of 50 degrees. And we would like to apply the work-energy theorem to get the work done on the box as it slides down the ramp. Well, a good first step is to set up a force diagram because there are forces involved. So here is the force diagram. There is a normal force that is perpendicular to the ramp. there is the force of gravity that is pointing straight down. We then ask what each of these forces do to create work. In order to do that, we have to identify the components of the forces that are pointing in the direction of motion. Let's choose reasonable coordinates. The reasonable coordinates are right here. Here's the x-axis along the ramp. Here's the z-axis perpendicular to the ramp. The angle between the x-axis and the horizontal is theta. We're going to want to split the gravity and the normal force into its x and z components. So let's see, this is the angle theta. That's a right angle. It's the angle between x and the z. This must be a right triangle in here. So there, double arc is the complement of theta, the other angle in that right triangle. And here is the angle theta again, because after all, horizontal and vertical are perpendicular to each other. So the sum of this angle and that angle must be 90 degrees, and that is the angle theta. We're taking the component of this object, where the arrow is along the line, that's the component of gravity in the x direction, and that component is clearly going to be the length of the hypotenuse times, since this is the opposite side, sine theta. Okay, let's look at the components. Number one, the x component of the normal force is 0 because the normal force is all along the z-axis. The work done by the normal force is integral over the distance traveled. There's the variable of integration. There's the component of the force parallel to the line of integration. But gee, n sub x is 0, so the work done is 0 joules. The x component of gravity, argument I just gave you, is mg sine theta, and therefore the work done by gravity is integral over the distance traveled, dx, times the x component of the gravitational force, which is mg sine theta. Once again, the components are scalars. Now we have to be a little careful. What is our variable of integration? Well, to know that, we look at the integral symbol, and we remember if it is an integral symbol, it has a d name of variable on it, in this case dx. M, g, and theta are all constants with respect to x. The angle of the slope does not change as we move along the slide, so theta is a constant, and therefore the x component of gravity is going to be when integrated, is going to be mg sine theta times x. Note that the sine theta stays as theta. It doesn't turn into a cosine theta. And we are integrating from x equals 0 to x equals 3. When we do that, and we plug in all of the numbers, here is the x, the distance we travel. There is the mass. There is the simple approximation for g. There is the sine 50. And the total work done is therefore 300 sine 50 joules. Okay, let's work down the page a bit. Here's the total work done. And now we'll apply the work-energy theorem. The work-energy theorem tells us that the total work done, which was only done by gravity, that's the only force in the direction of motion, is kF minus ki. Kf is 1/2 m times v final square. If I rearrange the work-energy theorem, I take ki to the other side, and I get that kF, here's kF, is the work done plus the initial kinetic energy. I can now solve for v sub f. I take the m and the 2 to the other side by multiplication, so I get a 2 over m here times w plus k. And this was a square. I took a square root of both sides. I'll point out something I don't usually point out in lecture, namely what I did to get to this point. when you see a transformation like this, you get to figure out to some extent what I did to get there. That's an extremely important skill, because if you're reading a journal article or a technical paper or technical manual or whatever, the author will probably not spell out very clearly what she or he did, and you have to work out that, well, the 2 got to the other side, that must have been multiplication. The m is now downstairs, that must have been division. And g, the square disappeared, and there's a square root. Okay, we've gotten to here, and we now plug in the numbers, and we get the final velocity, which you can evaluate. I'm now going to show this problem has another important part. The other important part of the problem is to demonstrate why it is useful to solve analytically. Namely, we've solved the problem here. Now suppose the initial velocity is 6 meters per second instead of 0 meters per second. That's where this 0 came from. The initial kinetic energy up here was 0. Well, if the initial kinetic energy is 6, you get to plug in 6 into the initial kinetic energy. We have already derived the general formula. I just duplicated the derivation in case people got confused, and therefore, in order to solve if the initial speed is this, because we did everything analytically, all we have to do is to plug in numbers again. And I've stretched this out so and expanded a bit, and you see that the 2 over m times the m over 2 in k final and in k initial cancel, and here is the formula for v final when v initial is given, and there is the answer, and we are done. And here we are with problem A-38. We have a mass. It's initially here at x, and I've chosen this to be x equals 0. We apply a horizontal push force to the mass, and under the influence of the push force, the mass is moved from x equals 0 to a distance in, which we've called x equals minus L. You could certainly use different notation. The motion is from here to here, and what you are told is that the mass moves very slowly over the entire distance. So we're asked what force is done by the spring, what force is done by the push force. The first point, which you could work around a bit, here's a piece of a force diagram. I've only labeled the x-axis implicitly, and there is the force due to the spring as indicated. There is the force of push as indicated. The force due to the spring must be a number of people needed to think about this a bit more clearly. The push force and the spring point in opposite directions. The spring force, if you look at it, is pointing in the plus x direction. So what is the spring force going to be? It's going to be minus kd. Bunches of people, alas, lost the minus sign. Remember, in this picture as drawn, and most of you did have it this way, the plus x-axis points to the right. We're moving to the left, the minus x direction. You see, this is a location I've called x equals minus L. And if the displacement of the spring, the compression of the spring, is a negative number, and we want a positive force out, we better have a minus sign here. The object moves very slowly, so the total force on the mass must be very close to 0. And in order for that to be true, the push force must be equal in magnitude and opposite in sign very, very nearly to the spring force. Notice I said very, very nearly. After all, the object has to start moving. It has to slow down at the end, and therefore the push force at different places can't be exactly equal to the spring force, because if it was, the object would never move. Okay, let us now calculate the work done by the spring and the work done by the hand on the object. So, the work done by the spring is integral over the spring displacement. I'm calling the displacement when we're partway in delta, and delta is a variable, and delta goes from the value 0 to the value minus L, and the spring force is minus K delta. There's a minus sign here. And therefore, integrate minus K delta, you get minus K delta squared. This is an integral. There is a 1/2 here, and we are evaluating from delta equals 0 to delta equals minus L. And when you do that, you have the value of this term at L minus the value of this term at 0, and there's a minus KL square over 2 minus, I didn't bother to write it out, but it's 0. What about the work done by the hand? The work done by the hand, the push force, is plus K delta very nearly. We are integrating over the displacement from 0 to minus delta. This integral is K delta square over 2, and when we evaluate over the distance we're going, we get a plus KL square over 2. We are evaluating and we end up at L. Notice that if you use the evil, depraved, wrong formula, work equals force times distance, you would have calculated the work done by these to be KL or K. Gee, it's a function, but you'll not think about that, times L, and you would have gotten the wrong answer. So the total work done from 0 to minus L, d delta, times what's the total force? It's 0 because the two forces are equal in magnitude and very nearly opposite in sign, so the total work done is 0. Aside. These signs are opposite. The work done by the hand is positive. It's work that is, the hand is attempting to accelerate the mass in the direction of motion. Of course, it fails because there's another force acting. The work done by the spring is negative. The spring is trying to slow the mass down as it moves from right to left. The spring, of course, in a certain sense, isn't doing anything because there's no kinetic energy at the start or the end. The net change in the kinetic energy, the work done, is 0. So inbound, the change in the kinetic energy, thanks to the work energy theorem, Kf minus Ki is the total work, is 0. What about what happens in the outbound direction? Well, let's shift to the outbound direction. In the outbound direction, the force of the spring is the same as it was before. It's minus Kd. Remember, delta is the change in the spring from its equilibrium position, and delta points in, delta is a displacement in the negative x direction, so delta is a negative number. So the force, it's pointing in the plus x direction, is surely going to be minus Kd, and the work done is the integral from minus L to 0 of minus Kd. Well, let's see, that's an integral of delta with respect to delta. That's minus K delta square over 2. The integral is taken from minus L to 0, start position, end position. So when you evaluate, you have a minus K0 square over 2. That's the final value of this integral. And you have a minus, because you subtract the initial point, minus K delta squared. Two minuses make a plus. K delta squared, but G, minus L square and L square are equal to each other, so the work done by the spring is plus K delta square over 2, where delta is equal to minus L. The change in the kinetic energy as the spring expands again is given by the work energy theorem as Kf minus Ki is the work done. So Kf is equal to the initial kinetic energy, which is 0, plus the work done. You see, I just took Ki to the other side. And the work done is K delta square over 2, where delta is equal to L. I have carefully warned the grader to look carefully for magic signs. Magic signs occur when you get one number with the wrong sign, and somehow mysteriously the sign which someone has noticed has to be wrong disappears before you get to the next step. I view this very negatively, I just do, and magic signs lead to serious point loss. Honest, they really do. So that is problem that we have just finished. And now we have reached problem A-40. Once again, our poor defenseless box is allowed to slide helplessly down a ramp. This time, however, the ramp has a coefficient of kinetic friction of 0.3. Because it has a coefficient of kinetic friction, the forces on the box are more complicated, but we can still ask what the work-energy theorem tells us about the motion of the box. So the first thing we'll do right here is to draw our force diagram. The force diagram shows each of the forces labeled, and it shows the coordinate system we choose to do. Since we are calculating the work done as we slide along the ramp, we are going to want to know the components of each of the forces parallel to the ramp, and it's therefore certainly convenient to choose one of our coordinate axes to match the components we're going to need. So there it is. Okay, so we have the forces acting, and we now need to break the forces into components to isolate the component of each force along the x-axis. We have done the component of gravity along the x-axis in problem A-37. Guess what? It's the same component that it was a few minutes ago. The force of gravity, here's mg, is pointing vertically downwards. Here is an angle theta. A certain amount of trig shows here is another angle theta, and therefore here is the component of gravity along the x-axis. It's mg sine of theta. The other two forces are much less painful, namely they actually lie along the x or z axes, and we are now kind of ready to calculate the work done. Almost. So we start out, and what is the work done by the normal force? Well, if you look at the picture, here's the normal force. It's pointing along the z-axis. It's perpendicular to the x-axis, and therefore the x-component of the normal force is 0, and the work done by the normal force is therefore integral dx from 0 to L of 0, g, it's 0. There is also the work done by gravity. The force of gravity has a component along the x-axis, and we have to be a little careful here because we have to put in the sign of the component, the plus or the minus. Is the force, the component of gravity, mg sine theta, along the x-axis going to be plus mg sine theta or minus mg sine theta? The sign, the plus or the minus, not to be confused with the sin sign, the plus or the minus is arbitrary and is determined by the direction of the component axis. It has nothing to do with the fact there's a minus here because I said in one coordinate system the component of gravity is going to be minus mg, the force of gravity is minus mg k hat for a different set of coordinates. No, the plus or the minus is determined by which way gravity is pointing with respect to this arrow, and the force of gravity, the x component of gravity, is pointed in the plus direction. So here there is a plus sign, and there is the integral for the work. So we're going to integrate, and as always, I remind you, when you have an integral, you must label the variable of integration, and you integrate with respect to that variable. So you would get an mg x sine theta. It's still sine theta. You didn't integrate with respect to theta. And when you evaluate from 0 to L, you get mgl sine theta for the work done by gravity. Now we have to calculate the frictional force. In order to calculate the frictional force, we need to know what the normal force is. In order to calculate the frictional force, we also have to know which way the box is moving, because, and we know it's moving downhill because you're told that, because the frictional force always points opposite to the direction of motion. If I gave you this problem and pieces of the diagram weren't there, so you didn't know whether the box was moving uphill or downhill, you wouldn't know which way the frictional force was going. Of course, someone, not in this class, you guys are really quite sharp, would ask, well, how can the box possibly be rolling uphill? And the answer is that at moments briefly before the start of the problem, I walked up to the box and gave it a stiff kick in the upwards direction, and it would still be sliding uphill at the start of the problem. That is not your problem yet. Hey, that'd be a nice exam problem, wouldn't it? It'd be amusing. In any event, we're going to have to calculate the normal force, and to do that, we apply the second law. And the second law tells us the sum of the forces in the z direction are equal to m times the z acceleration. So what are the forces in the z direction? Well, there's an n plus n, and there is the component of gravity in the z direction, and that has a minus sign in it. We'll go back and look at the picture again and see that I put in the correct sign, the minus, for the force of gravity. Let's do that. Here is the picture. Here's the force of gravity pointing along the arrow. So the component of gravity in the z direction is this component, mg cosine theta, and now we have to compare the direction of this component, it's pointing it over here, with the direction I happen to have chosen for the z-axis. You see the direction I chose, and therefore this component of gravity is minus mg cosine theta. That minus is determined by this direction and has nothing to do with this minus sign. Okay, but we're sliding along the ramp, so our motion in the z direction perpendicular to the ramp is 0, and therefore the z acceleration is 0. That's a nice feature of this coordinate system. And therefore the sum of the forces in the z direction is 0. Here is our correct value for n. The work due to friction is then integral force, here's the force, dx. And if you look carefully, you will observe that there is a minus sign here. That minus sign occurs because the friction force points in the minus x direction, and I have put in the various terms correctly. So here is the friction force. I integrate from 0 to L, and therefore the work done by friction is negative. That's, by the way, is an important check. The work done by friction, because friction always opposes the direction of motion, the work done by friction is negative, and therefore the total work done is the sum of the various terms is this. So here's the total work done. Now we're asked what the final velocity is. And we flip ahead, and we are going to apply the work-energy theorem, which is Kf minus Ki is the work done. I'll take Ki to the other side, and now I'll substitute. Here's the final kinetic energy, 1/2 mvf square. Here's the initial kinetic energy, 1/2 mvi square. And here is the work done. And having written out the equation, I've made two improvements. I've divided out a common factor of m from every term. Here, 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 and here. And I multiplied both sides of the equation by 2. That cancels this half. That cancels this half. It inserts a 2 here. It inserts a 2 here. I now have a formula for Vf squared. I take the square root, and here is our algebraic formula for V sub f. I will now remind you why it is so superior to solve problems analytically rather than numerically, other than the fact that there is massive point loss for plugging in numbers at the start of solutions. Namely, If I want to solve for start at rest, I just stick in the numbers and solve. If I want to solve for start at 6 meters per second, I just stick in the numbers. This number happens to be different, and I solve. And the solution process up to here, all the work has been done. All I do is stick in two sets of numbers which are different at one point. We are now done with problem A-40. We are now done with the class. The Phillies Emergency Teaching Network is now going to leave the air.